In this video, we will use the inverse tangent function to determine the radian measure of an angle given the slope of the terminal ray of that angle. So consider the following context. We have an angle here, and we want to know the radian measure of this angle theta. So if we want to use the inverse tangent function, we need to recall that the tangent function itself outputs the slope of the terminal ray. So if we want to know the slope of this terminal ray, we can use the terminal point's location. In this case, the terminal ray has a slope of 1.83 divided by 0.82. And that's just because this terminal ray is 0.82 units to the right of the center of the circle and 1.83 units above the center of the circle. So to compute the slope, we compute the change in y divided by the change in x, which looks something like this. And this slope has a value of about 2.23. So the slope of the terminal ray is about 2.23, in which case we can say that tangent of theta is equal to 1.83 divided by 0.82, which is that value of about 2.23. So the inverse tangent function will take that slope as its input. So inverse tangent will take that slope as an input, and it should output the value of theta, or the radian measure of that angle. And if we plug that into our calculator, we should get a value of approximately 1.1495, something around there. If we look back at our diagram, this angle does appear to have a measure of about 1.1495. So this value for theta is the value we're looking for. Let's look at another example. So we have a similar context where we have an angle whose initial ray points in the 3 o'clock direction, and we know the coordinates of that terminal point. So again, if we want to know the slope of that terminal ray, the slope, m, is equal to 1.86 divided by negative 0.74. So that ratio will compute our slope, which is about negative 2.51. So that terminal ray has a slope of about negative 2.51. And if we use the inverse tangent function, so we tangent inverse of that slope, 1.86, divided by negative 0.74, we should get a value of approximately negative 1.19. We'll throw a 2 in there as well. Now we should be a little alarmed by this. The angle we're looking for needs to be between 0 and 2 pi, and the angle we're looking for doesn't appear to have a negative value. So what does this negative 1.192 tell us? Recall that the inverse tangent function will take a slope of a terminal ray, so it'll take this slope right here, and it'll output the angle whose terminal ray points to the right-hand side of the circle. So it's going to give us the measure of that angle right there, and it's going to give us the negative version right there. So it's going to give us an angle between negative pi divided by 2 and positive pi divided by 2. So this negative 1.192 is the measure of that angle right there. So to use this negative 1.192, we should imagine starting at the 3 o'clock position and then rotating half of a full rotation. So start at the 3 o'clock position and imagine sweeping out a half of a rotation so that we end up at pi radians. So we'll start at pi radians, and then if we rotate an additional negative 1.192, which would move us in the clockwise direction, so if we went a negative 1.192 radians, that would take us back to theta. So we start at pi radians, and then we swapped out an additional negative 1.192 radians, and that got us back to theta radians. So in this case, theta, the measure of our angle, is just equal to this pi, and then minus the 1.192. And that has a value of approximately 1.949. If we look at our diagram, a radian measure of about 1.949 matches up with the situation we're looking at. So keep in mind that the inverse tangent function takes the slope of a terminal ray as its input and then outputs a radian angle measure between negative pi divided by 2 and positive pi divided by 2, so that the terminal ray that it gives us points to the right half of the circle. So sometimes, if our terminal ray is to the left of the circle, then we'll have to do a little extra work to find the actual radian measure of the angle we're looking at.